Today we will see few problems that we solve using the Hamiltonian and the Hamilton's canonical equations. The problems that we are going to see are those we have solved using Lagrangian mechanics. Same problems we can solve using the Hamiltonian, in the Hamiltonian formulation using Hamilton's canonical equations. Okay, so let's begin with the simple pendulum. We are asked to write the Hamiltonian for a simple pendulum and deduce its equation of motion. Here the kinetic energy that is given by half m L square theta dot square. We know what is L. L is the length of the pendulum. Okay, the pendulum is swinging. This is the equilibrium position. It's swinging and it is at the position A at some instant. And this angle is theta. And we have already seen the kinetic energy can be written T as equal to half m L square theta dot square. Okay. And the potential energy, that will be mgl 1 minus cos theta. Okay, the potential energy that is given by mgl 1 minus cos theta with respect to this equilibrium position. So this is the kinetic energy, this is the kinetic energy and this is the potential energy. And Lagrangian we know T minus V, kinetic energy minus potential energy. So this is half m L square theta dot square minus mgl 1 minus cos theta. So this is Lagrangian. Now we determine the canonical momentum for the variable theta. We have only one variable here, only 1 degree of freedom in the case of simple pendulum. Theta only, L is the length, that's fixed. So the generalized momentum corresponding to this theta dot, or for the theta, okay, for the theta that is given by p theta, the generalized momentum corresponding to theta, this dou L dou theta dot, which is ml square theta dot, and theta dot is p theta by ml square. Okay, so p theta, that is ml square theta dot is this. And how do we find the Hamiltonian? Using this sigma j pj qj dot minus L. We have to sum over all the variables, generalized coordinates, that is sigma j pj qj dot. Pj is the corresponding canonical momentum, qj dot the velocity, minus L the Lagrangian. Here we have only one variable, only theta. So in this summation we need to take only one, pj and qj dot. Pj is given by p theta, that is ml square theta dot, that is written here, qj dot is theta dot, and L is this half m L square theta dot square minus mgl 1 minus cos theta. So this is L. And we have this, when you combine this and this, you have this half ml square theta dot plus mgl 1 minus cos theta, and this is clearly the total energy, because this is the expression for kinetic energy and this is for potential energy. So T plus V, that's the total energy. We know for the conservative systems, Hamiltonian is the total energy of the system. Okay, and we express is theta dot in terms of p theta, using p theta, because the Hamiltonian we always have the generalized momentum and generalized coordinate. So we express theta dot like this, and so we have p theta square by 2ml square here, and here we have mg L1 minus cos theta. So this is the Hamiltonian. So for theta dot, we know theta dot is the what? P theta by ml square. So that we substitute, and we have this, then this is the Hamiltonian. Okay, Hamiltonian H is given by this. Then the Hamilton's equations. Hamilton's equations. We have only one coordinate, 1 degree of freedom. So 2 Hamilton's equations. We know there will be, if there are n coordinates, there will be 2n equations. Here we have only 1 equation, so 1 coordinate, and we have 2 equations. Theta dot is given by dou h dou p theta, okay, which is p theta by ml square. Here we take dou h dou p theta. So as we differentiate, you will be getting p theta. This is p theta square. So 2 p theta we will get. That 2 will get cancelled, and we have what? P theta by ml square. And p theta dot, that is minus dou h dou theta, we know. Okay. For h is this, and with respect to dou theta we differentiate, so this will be sin theta, so minus mgl sin theta here. Okay. We have 3 minus signs here. Minus sign, as you differentiate cos theta, you will get minus sin theta, and additional minus sign here, minus dou h dou theta, so we have minus mgl sin theta. So this is theta double dot plus g by l sin theta equal to 0. So theta double dot plus g by l theta, that is equal to 0. For small theta, as we always make this approximation, for small theta, sin theta is theta, so theta double dot plus g by l theta is equal to 0. And this is the equation of motion of the pendulum. Okay, that we already obtained using the Lagrangian mechanics. So this is the equation of motion of the simple pendulum, and from this you can get the time period, everything can be obtained. Now let's move on to the second one, the Hamiltonian for linear harmonic oscillator. The same procedure that we follow. We have the kinetic energy as equal to half mx dot square, potential energy as equal to half kx square. In this one also we have only 1 degree of freedom. So kinetic energy is given by potential. So L is T minus V, is half mx dot square minus half k x square, the Lagrangian, and we find the momentum dou L dou x dot, that is equal to mx dot, and x dot is given by px by m. And this Hamiltonian, that is given by the sigma j p j q j dot, this is px x dot. We have only one variable, so px x dot minus half mx dot square minus half kx square, the Lagrangian. Okay, and for x dot we can give what? X dot is px by m. Okay, x dot is px by m. So that we substitute here, and we have the px square by m here, and as it combines with this, here we substitute for x dot. So we have this, we finally get half px square by m, or px square by 2m plus half kx square, which is the T plus V, the total energy of the system. Okay, so this is the Hamiltonian. So Hamiltonian, that is given by the total energy T plus V, like this. Hamilton's equations. Hamilton's equations are given by x dot equal to dou h dou px. Okay, x dot, that is dou h dou px, and px dot equal to minus dou h dou x. These are the two equations, okay, for the Hamilton's equation. So x dot dou h dou px, that is px by m, okay, px by m. As you differentiate this, you will get px by m. Px square is there, so as you differentiate, and here px dot is minus dou h dou x. As you differentiate, you will be getting minus kx here, and px double dot, that will be px dot is, px is, x dot is px by m. So px dot is what? Px dot is x double dot m, okay. Px is x dot m, so px dot is x double dot m. So we substitute for that, and mx double dot minus kx, and we have x double dot plus k by mx, x equals 0. So this is the equation for the linear harmonic oscillator, okay. So using Hamilton's equation, we can obtain the, so that's the oscillator, one-dimensional oscillator. Now we have the two-dimensional harmonic oscillator. So what will be the difference? We will have two variables, x and y. This is a two-dimensional harmonic oscillator. So we have two variables, x and y, and the Lagrangian is given by this half m x dot square plus y dot square. The kinetic energy corresponding to the two variables. The potential energy is given by this. So this is just a simple extension of the one-dimensional harmonic oscillator. And px is dou L dou x dot, that is mx dot, and x dot is px by m, and py, we know dou L dou y dot, generalized momentum corresponding to y, dou L dou y dot, that is my dot, so y dot is py by m. So h is sigma j pj qj dot minus L, h sigma j pj qj dot minus L, and which is px x dot plus py y dot. L is this half m x dot square plus y dot square minus half k x square plus y square. Px dot x dot is px square by m, because the x dot we know we have got as px by m. So this is px square by m, and we have here y dot we know py by m, so py square by m, and for x dot also we y dot we substitute, and that will finally give you px square by 2m plus py square by 2m plus half k x square plus y square, and this is the total energy. Okay, and this is the total energy of the system. So Hamilton's equations, now we are writing x dot as dou h dou px, that is px by m, and px dot is minus dou h dou x, which is minus kx. Y dot is dou h dou py, which is py by m, and py dot is minus dou h dou y minus ky. So this is so straightforward. You can obtain just by differentiating, partially differentiating with respect to px and px py and xy. You can see, get this, and we know px dot, since x dot is px by m and px will be x dot m, okay, px x dot m, or similarly py, that is y dot m. So as we substitute, we have this mx double dot plus kx is equal to 0, my double dot plus ky equal to 0. So these are the equations of the motion. So two equations that we get for the simple harmonic, two-dimensional simple harmonic oscillator. Okay. So in all these problems, we have followed the same procedure. We wrote the Hamiltonian And then from the Hamilton's equations, we obtain the equations of motion. Now suppose you are directly given a Lagrangian. This is a Lagrangian, ax dot square plus by dot square minus kxy. So we have two variables, x, y. So there will be four equations of motion, Hamilton's equations of motion. So you have to obtain the Hamiltonian and then the equations of motion. Okay.